This is problem 22 of the QHack 2023 Quantum Coding Challenges, and this one is entitled Entangled Robot Swarms. Now in this problem, what we're being told is that we have a qubit in our possession, and we want to entangle that qubit with 3 more qubits that are going to be in the possession of some robots. So basically here we're going to prepare an equal superposition of the state 0, 0, 0, 0 plus 1, 1, 1, 1. And obviously, if for some reason any of these qubits gets measured, then that superposition is going to collapse to either the state 0, 0, 0, 0 or the state 1, 1, 1, 1. And what we want to do is to prevent that from happening. So we want to avoid collapsing the whole superposition. So we're asked, well, if these robots have some sort of way of detecting what will cause the measurement and will cause the superposition to collapse and apply some sort of unitary, what would that unitary be? And what would we have to do after performing the measurement to preserve the original superposition of the remaining qubits to set up a new robot that would now allow us to keep that equal superposition of 4 qubits in state 0, 0, 0, 0 plus state 1, 1, 1, 1. So let's take a look at this step by step in a circuit to make it a little bit clearer. So again, we start with an equal superposition of the state 0, 0, 0, 0 and state 1, 1, 1, 1. And we can create that using GHZ state preparation circuit. So basically a Hadamard gate followed by the CNOT gates. And then it's not very difficult to show that if we apply a Hadamard gate here in this qubit before performing a measurement to that qubit, well, we end up with the state now 0, 0, 0, 0 plus and 1, 1, 1 minus, which is equal to, well, again, 0, 0, 0, and then this is state plus and 1, 1, 1 is state minus, just in the computational basis, which now if we factor the zeros here and the ones here, we end up with the superposition state 0, 0, 0, 0, 1, 1, 1, 1, and then a 0 here, and then the same state here but with a minus. So basically this is like having what we're going to call here the state 5 plus 0 and the state 5 minus 1. So if you see here, we've managed by applying the Hadamard gate to separate this state 0 and 1 and an associated state that only differs by a phase on the 1, 1, 1, 1 state, right? And now if we were to perform a measurement, then we will get with 50% probability this state 5 plus 0 and with 50% probability 5 minus 1. So now we have 2 choices, but at least the 3 qubits on which we didn't perform a measurement still remain in a superposition. All we need to do is find a way to make them equal. Well, if we now apply a Z gate to one of the qubits that would still remain in superposition, conditioned on the qubit that got measured, right? So if we measure a 1, then we apply that Z gate, well, that's gonna turn that phase on the 1, 1, 1 state to a plus. And then here on these 3 qubits, we end up with always with this state 5 plus, which is the equal superposition of 0, 0, 0 and 1, 1, 1. And then, well, if now we have another qubit, that's going to be our last robot, let's say, right? And we just take any of these other qubits, let's say the one that is in our possession, and just apply a CX gate. Then now we're going to have overall our state 1 over root 2, 0, 0, 0, 0, plus 1, 1, 1, 1, right? So there is a way to create a new superposition with a new, let's call it robot here, to restore the one that got measured. So that's it. So let's go ahead and get this coded in PennyLane. So we import PennyLane and NumPy. And then here I'm just going to use the same function names that are used in the challenge. So first we need a function called bell preparation, and that's just a Hadamard gate. And here I'm using this broadcast function that would allow us to generate this cascade of CNOT gates by using this pattern chain. So just to show you what we would get is if I just print that circuit with, let's say, 4 qubits, then it creates the Hadamard and then the cascade of CX gates. I can also do it for any number of qubits here. Then we are going to generate a function called emergency gate, which, as we saw, is just applying a Hadamard gate to whichever wire is the one associated with a robot that is about to get compromised. And then we just need to define a function called setting new robot, which is going to be a conditional gate, assuming that the output of the measurement is 1, to apply a poly-Z gate on that new robot wire, and then that CNOT gate that entangles the remaining states with the new qubit. Okay, and then the last part of it is just some code that is given to us already that will put everything together. So basically we have wires that have the names associated with our qubit, which is called hub, robot 1, robot 2, robot 3, and then the new auxiliary robot. Then it calls the bell preparation state. I have added a barrier here to just make it clear to display. Then we apply that emergency gate to the robot that is about to get compromised. Then after that emergency gate, the measurement happens, and then we set up the new robot conditioned on that measurement that it's performed. So if we now draw that circuit, we can say here the GHZ preparation circuit, then the Hadamard gate that will allow us to separate the superposition state based on the 0 or the 1. Now in the example, that measurement and Hadamard was being applied to the last robot, but it doesn't matter where it happens. It's the same concept, it's just on a different qubit. And after that, a measurement will be performed, and depending on the result of that measurement, this Z gate will be applied to the hub state, and then a CX gate to entangle that new robot. And just to show that our circuit is implemented correctly, I'm going to copy and paste all the greater functions that are used in this problem. And here, if we run it, you can see here that we get the correct solution. So I hope this was clear. Please let me know if you have any questions.